You're here because you want to get smart, fast. You crave those moments where complex ideas just click, where you suddenly see how things connect without getting totally bogged down. That's really the sweet spot we aim for in each deep dive. And today, well, we're tackling a big one, the search for a theory of everything in physics. Now, your mind might jump straight to quantum gravity, and yeah, that's definitely part of the picture. But a true TOE, it strives to go further, to elegantly unify everything, from the tiniest particles in the standard model to the huge cosmic scale of Einstein's General Relativity.
Absolutely. I mean, the underlying quest is really to find the fewest possible fundamental ingredients, the simplest assumptions, that can then naturally give rise to this incredibly rich and diverse universe. We see, all the different particles, the forces, how they interact, everything. It's really about finding that deep simplicity hidden inside all the complexity.
And that brings us squarely to geometric unity, or GU. It's a fascinating attempt at a TOE proposed by Eric Weinstein. Now, diving into the material around GU, that's a serious undertaking. It represents a huge amount of intellectual effort. You could maybe compare it scale-wise to something as intricate as string theory.
It's true, yeah. Geometric unity can seem pretty daunting at first glance. However, the core concepts actually build upon really well-established ideas in differential geometry. The real innovation, you see, lies in how these familiar tools are put together and the new language, the terminology used to describe these combinations. For someone with a solid grounding in mathematical physics, say at a graduate level, the underlying ideas are definitely within reach.
Okay, so in this deep dive, think of us as your guides through this landscape. We'll kick off with a high-level view. What's GU trying to achieve? Then, we'll remind ourselves of the current picture modern physics as it stands. That's the target GU is aiming for. From there, we'll dig into some of the crucial ideas at the heart of GU itself. And finally, we'll try to loop back and see how it all connects, or aims to connect, back to the physics we, already know and love.
Think of it like this. First, identify the target. Then understand the tools being used. And then we see how those tools are actually deployed to, hopefully, hit that target.
Right. Now, Eric Weinstein has offered a few very short summaries of GU. One that gets thrown around is just 4 words. Einstein knows potty salon. Okay, unless you're already pretty deep in particle physics lingo. That probably doesn't tell you much. Then there's a slightly longer one, 30 words. General Relativity Grand unifies the standard model's first generation by pulling back Weil spinor for the space of metrics after trace reversing the Frobenius metric on the fibers. Shit. All right, that one's definitely speaking to a very specific audience. You need a strong background in advanced math for that one.
Yeah, those very concise summaries are really more like pointers. Pointers to the sophisticated mathematical structures that are really operating inside geometric unity. The 30-word version, it touches upon key elements, right? The idea of working with the space of all possible shapes of space-time, the metrics, and the fundamental quantum building blocks, the spinors, those are central ideas in the theory.
What's really interesting to think about is how our current physics understanding evolved. The argument Eric makes is that quantum field theory, which is, the bedrock of our particle and force understanding, has been super heavily reliant on analysis, calculus, related techniques, and maybe, just maybe, this focus led us to overlook some really important geometric, topological, algebraic aspects of reality. I mean, thinkers like Jim Simons, Edward Witten, they've been championing this more geometric view in physics for decades now.
That's a crucial insight, absolutely. While the analytic approach has been, incredibly powerful, incredibly successful, it's possible that by prioritizing it, we might have missed some deeper structural principles that only geometry can reveal. Often, you find geometric frameworks can offer more elegant, more unified solutions to problems that seem, really tough from a purely analytic angle.
Just to give you a taste of what we mean, here are 5 puzzles in physics. Things that don't seem to have easy answers in a purely analytic world, but where geometry might offer clues. We won't solve them now, just food for thought. First, how do we avoid these weird mathematical objects called pseudotensors? They behave oddly under coordinate changes. Second, in quantum mechanics, how do we guarantee probabilities always stay positive? They can't go negative, right? Third, how can we systematically spot these things called anomalies in quantum field theory? They can break the whole theory's consistency. Fourth, what's the deep origin of non-local spectral contributions? These things that seem to connect points across distances kind of mysteriously. And finally, how do we even start to build a consistent quantum theory on the curved space-time Einstein described?
These are all really profound, challenging questions. They highlight potential limits in our current toolkit, and they underscore the potential for, a geometric way of thinking to maybe open up new avenues.
Okay, now let's zoom out. Let's look at what a successful theory of everything should, ideally, be able to derive. Think of these as the fundamental ingredients of the universe as we currently understand it. The things our best theories describe. It's like DNA-based pairs. Simple in themselves, but they generate all the complexity of life. So first ingredient, Einstein. This is shorthand for the Ricci curvature tensor. It's a mathematical object derived from the even more fundamental Riemann tensor. What's maybe a bit peculiar is how it's defined, related to certain antisymmetry properties of the Riemann tensor. But intuitively, the Ricci tensor tells us how the volume of a tiny region of space-time changes because of its curvature. It's basically describing gravity.
The Ricci tensor is absolutely the central player in Einstein's general relativity, yeah. It mathematically captures how mass and energy warp space-time's fabric, leading to what we experience as gravity.
Okay, next up, Yang-Mills-Maxwell. This represents the mathematical framework for gauge fields. Here, the field strength, think of it as a kind of generalized curvature, is tied to something called a gauge connection. This framework is what we use to understand the fundamental forces: electromagnetism, the weak nuclear force, the strong nuclear force.
Right. These gauge theories are the bedrock of how we understand fundamental particle interactions. The concept of curvature here is, well, more abstract. It goes beyond space-time curvature to describe the geometry of these internal spaces linked to the forces.
Then we have Dirac. This refers to the mass-describing fermions, the matter particles like electrons, quarks. They all have this property called spin 12. It involves a specific operator, the Dirac operator.
The Dirac equation, yeah, it's a cornerstone of relativistic quantum mechanics. It describes how these fundamental matter particles behave at high energies near light speed.
Following that, we have Higgs. This represents the math involving the Higgs field, a field permeating all of space, responsible for giving other particles their mass through interactions with it.
The Higgs mechanism is a crucial piece of the standard model puzzle, definitely. It explains how elementary particles can have mass without breaking the underlying symmetries of the theory.
And then Yukawa coupling. This is a specific term in the equations. It describes how the Higgs field interacts with fermions. The strength of this interaction sets the fermion's mass.
The Yukawa couplings are basically the knobs that set the masses for the fundamental matter particles. Their exact values, where they come from, still a big area of research.
We also have spin 12, mathematically represented by something called SL2C. That's the double cover of the proper orthochronous Lorentz group, SO plus 103. Okay, that's a mouthful. But essentially, it's the mathematical structure you need to correctly describe how particles with half-integer spin behave in spacetime. Think of it as a more refined way to handle rotations and boosts for quantum particles.
The Lorentz group describes space-time symmetries in special relativity. Its double cover, SL2C, is necessary. It provides a consistent framework for particles with that intrinsic angular momentum we call spin.
Next on our list, SU3, SU2, AU1. This cryptic sequence is the gauge symmetry group of the standard model. It encodes the fundamental symmetries behind the strong force, SU3, weak force, SU2, and electromagnetism, U1.
This specific combo of symmetry groups has been incredibly successful. It describes the forces and the whole zoo of particles we've found. A truly unified theory would ideally explain why nature picked this particular set of symmetries.
We also have family quantum numbers. These are intrinsic properties that help distinguish particles within a generation. Think of them like labels, helping categorize the basic stuff of matter.
Right, things like baryon number, lepton number, they're conserved in interactions. They help us understand the rules governing how particles interact and transform.
And speaking of categories, we have 3 generations of matter. We found that particles like electrons and quarks aren't unique. They come in 3 similar but heavier flavors, like the electron, muon, and tau. Why 3? That's a real puzzle.
The existence of these 3 seemingly redundant generations, each heavier than the last. It's one of the major unanswered questions in particle physics. A TOE might explain this triplication.
Then there's the CKM matrix, a mathematical object explaining why quarks can change flavor, like a down quark turning into an up quark during weak nuclear decays.
The Kabibo-Kobayashi-Maskawa matrix, yes. It mathematically describes this quark flavor mixing, essential for understanding weak interactions like radioactive decay.
And finally, the PMNS matrix. Plays a similar role, but for neutrinos. Explains how these sneaky particles can oscillate, change between different flavors as they travel.
The Pontecorvo-Makinakagawa-Sakata matrix describes that surprising neutrino oscillation phenomenon, where neutrinos just spontaneously change type as they fly through space.
Okay, wow. All these ingredients, they fit into 2 incredibly complex sets of equations. Einstein's field equations for gravity, and the standard model Lagrangian for everything else. And this is where Eric Weinstein points to what he calls the twin origin problems. He sees these intriguing mathematical similarities, analogies, between Yang-Mills theory, forces, and general relativity, gravity. For instance, gauge potentials in Yang-Mills are mathematically kind of like the metric tensor in GR. The big question is, can we derive these similarities from something even more fundamental? And crucially, can we do it in a way that respects gauge covariance? That's something the standard way of defining gravity using the Einstein tensor doesn't naturally do.
This is a very deep point. The fact our two best theories show these tantalizing analogies. It suggests there might be a deeper underlying framework unifying them. The challenge is finding that framework in a way that resolves the tensions, like that lack of obvious gauge covariance in GR.
And this brings us right to the central idea of geometric unity, the possibility of unification not by adding more layers, more complexity, but by realizing that all these seemingly separate ingredients of physics might actually just arise from inherent geometry of a basic four-dimensional space. Let's call it X4.
The beauty of this approach is its potential minimality. Start with a relatively simple geometric foundation and see if it can naturally generate the full richness, the complexity of the physical world. That would be truly elegant.
Okay, so let's start peeling back the layers of geometric unity itself. Layer 2, maybe? It all starts with step 1, the observer's construction. The most fundamental starting point, a four-dimensional manifold, X4. Think of it as the basic stage for physics. Crucially, at this initial stage, we don't assume any pre-existing metric or connection. No notion of distance or curvature on X4 yet.
That's a significant departure from many standard approaches, right? Where a background spacetime structure is often just assumed from the get-go. GU aims to build up spacetime itself from more fundamental principles.
Now, we introduce something called the metric bundle. Let's label it Y14.
Yeah.
This is a 14-dimensional space. Here's how it's built. At every single point in our original X4, we attach the space of all possible symmetric bilinear forms at that point. Now, a symmetric bilinear form, that's basically a way to define a metric. It tells you how to measure distances, angles. In 4 dimensions, there are 10 independent components to such a form. So for each of the 4 dimensions of X4, we have these 10 possibilities, plus the 4 dimensions of X4 itself. That gives 14 dimensions for Y14.
Right, so instead of picking one specific geometry for spacetime right away, geometric unity considers all possible local geometries simultaneously at every point in X4.
This is a really key idea because, one challenge in physics has been that our description of matter particles, especially spinors like electrons, often requires a predefined metric just to make sense. Creates a bit of a chicken and egg problem.
Yeah.
Especially thinking about quantum gravity, where the whole idea of a fixed space-time geometry might break down at the smallest scales. How can you have matter if you don't have a well-defined space-time to put it in?
Exactly. By working with the space of all possible metrics, GU tries to get around this issue. The hope is that fundamental things like spinors can be defined in this more abstract setting, in a way that doesn't depend on picking one specific spacetime geometry first.
A crucial innovation here is the chimeric bundle. It's a mathematical structure built by combining 2 other things. The vertical bundle, which captures how the metric can change at a single point in X4, and the dual of the horizontal bundle, which relates to moving between points in the base space X4.
This specific mix of vertical and horizontal parts in the chimeric bundle, it's designed to bridge the gap between internal symmetries of particle physics and the external symmetries of space-time and gravity.
Now, the vertical space, those metric variations, at one point, it naturally gets a way to measure the distance between different metrics. That's thanks to the Frobenius inner product. Think of it as a natural ruler within the space of metrics at a point.
The Frobenius inner product provides a mathematically natural way to quantify the difference between 2 infinitesimally close metrics at the same spot in X4.
Okay, what about the horizontal space? The part about moving around in X4? Well, its structure comes from choosing something called a connection. And this is how, within this framework, it becomes possible to define the math needed for spin particles, even without having a fixed metric on X4 to start with. At this stage, the underlying symmetries of GU are related to some pretty big complex groups, spin 7,7 or spin 5,9, which leads to a complex spinor representation with 64 components.
The emergence of these specific spin groups and their representations is key, because these mathematical structures potentially have room to fit the particles and forces we see in the standard model.
Moving on to step 2, the frame bundle and its double cover. Okay, back to our original space, X4. At each point, imagine all possible sets of 4 independent basis vectors for the tangent space there. Think local coordinate systems or frames. The collection of all these frames over all points of X4 forms the frame bundle. Mathematically, the relationship between different frames at the same point is described by the group GL4-8R. Standard stuff in differential geometry.
The frame bundle gives us a way to describe the local orientations, the sort of texture of the manifold at each point. It's a fundamental tool for working with vectors and tensors.
Right, a frame is just an ordered set of these tangent vectors. We can switch between frames using transformations from GL4. But here's the subtle issue. It turns out GL4 itself doesn't have nice finite dimensional representations that can describe spin particles. Essentially, if you try to find a matrix in GL4 that squares to -1 a math requirement for spin, you hit problems with real numbers.
Yeah, this is technical but crucial. The math properties of GL4 stop us from directly building representations for that intrinsic angular momentum, the spin of particles like electrons.
The way around this, move to the double cover of GL4, known as the metalinear group. It's a more sophisticated group, closely related, but it does have the properties needed for spinor representations. Using this metalinear group, we can construct the lifted frame bundle over X4.
Passing to the double cover basically introduces a kind of finer-grained view of the transformations. It allows for a consistent mathematical description of these spinorial objects.
Okay, next up, step 3. Construct observation maps. These are essentially ways of probing our fundamental space X4 using that metric bundle Y14. An observation map is a local section, meaning it takes a small region of X4 and assigns to each point in that region a specific metric from the space of all possible metrics, Y14. So it's like choosing a particular way to measure distances and angles locally.
You can think of these observation maps as different perspectives, or maybe gauges,
Right.
ways we can view the geometry of X4. Each map picks out a specific space-time geometry in a local region.
Okay, for any such observation map we choose, we get a pullback map. This is a mathematical operation allowing us to take geometric structures living on the bigger space Y14, like our spinor bundles, and bring them back down to X4, as defined by the specific metric chosen by our observation map. Think of these maps as tools connecting the abstract world of all metrics with the concrete reality of a particular space-time geometry. Now, this is where the spin bundle pops out. For any given metric at a point in Y14, which is metric on X4, remember, we can define a bundle of orthonormal frames, special basis vectors, right angles, unit length according to that metric. This bundle has SO1 point symmetry, the Lorentz group. And here's the key bit. This SO13 bundle naturally has a double cover, which is our familiar spin bundle, the structure that truly knows how to represent spin 12 particles in relativistic spacetime. This spin bundle has a 14-dimensional matrix representation, 10 components in the vertical part, metrics 4 from the dual horizontal part, movement in X4. This is our chimeric bundle C, now with metric. And interestingly, part of this chimeric bundle is mathematically the same as the 14D tangent bundle of Y14 itself.
This step is crucial, absolutely. It's where the connection to familiar relativistic spacetime with its Lorentz symmetries spin representations starts to emerge, emerging from that more abstract setup involving the space of all possible metrics.
Moving to step 4. Construct the tangent bundle and its dual. Okay, think about Y14, our 14D space of metrics over X4. At each point in Y14, there's a 14D tangent space, Ty. 10 dimensions correspond to ways the metric can vary, symmetric matrices. 4 come from the underlying X4. We can also consider the dual tangent space, Ty, the space of linear functions on Ty. Remember, a point in Y14 is like a pair, xg. X is a point in X4, G is a metric there. It turns out the part of Ty for changes in G at a fixed X, the vertical tangent space, is mathematically equivalent to the space of symmetric zero-2 tensors on X4, which are basically metrics, important point. Different physical fields will naturally live in either Ty or its dual Ty, and these two spaces aren't automatically interchangeable without more structure, like a metric on Y14 itself.
That distinction between tangent and cotangent, or dual tangent bundles, is fundamental in geometry. Reflects the difference between vector-like and covector-like quantities. They transform differently under coordinate changes.
Now, step 5, vertical bundle and Frobenius metric. Let's focus on the vertical bundle. As we said, the part of Ty tangent to the fibers of the metric bundle. A fiber is all possible metrics at a single point in X4. So the vertical bundle captures directions the metric can change while staying at that same point X. The Frobenius inner product gives a natural way to measure the size or distance between these different metrics at that point. Mathematically, trace of the matrix product of two symmetric matrices representing these tiny metric changes. Imagine a path through the space of metrics at a point. The velocity of that path is an element of this vertical tangent space.
The Frobenius inner product is a very natural choice for a metric on the space of metrics. It respects the underlying algebra of symmetric matrices, gives a well-defined way to measure variations in the gravitational field, essentially.
Next up, step 6, the Zorro construction. Okay, cool name. It refers to a specific procedure, visually like a backward Z. It provides a canonical, meaning natural, no arbitrary choices way to split the tangent bundle Ty into the vertical part, changes in metric, and a horizontal part. Horizontal means directions somehow parallel to the base space x4. This construction uses a symbol, looks like Hebrew gimel or iota, representing a metric choice on x4, local or global. Also uses the Levi-Civita connection, the unique parallel transport definer once you have a metric. Using these, the Zorro construction induces a metric on y14 itself via the Frobenius inner product. From this y14 metric, we get a unique Levi-Civita connection on y14. This whole process naturally splits Ty into vertical and horizontal bits, gives a well-defined way to lift vectors from x4 up to y14 without arbitrary choices. The horizontal subspace is the space of these lifted vectors.
The Zorro construction is pivotal in GU, provides a non-arbitrary link between x4's geometry and y14's richer geometry. The idea of lifting lets us systematically transfer geometric information and structures between these two spaces.
Let's revisit step 7, the chimeric bundle. Remember this key player. We can understand its structure better now.
Yeah.
Decomposed into vertical components, metric changes, and the dual of the horizontal components related to moving at x4. Importantly, choosing this horizontal subspace is equivalent to choosing a connection, which implies curvature. We saw the Frobenius inner product gives a metric on the vertical part. The fact that chimeric bundle uses the dual horizontal bundle, not the horizontal one itself, that's a crucial asymmetry, turns out to be necessary for eventually unifying gravity and the other forces.
The subtle asymmetry in constructing the chimeric bundle, it's a deep mathematical insight, plays a vital role in the theory's potential to unify gravity and gauge interactions.
Step 8. The Frobenius inner product is then applied to this chimeric bundle C at each point in y14. When we do this, the resulting structure decomposes into a part behaving like a trace, a single number, and a traceless part. The traceless part has a specific mathematical signature, 3 and 6. The trace part contributes either 1 or 0, 1, depending on a choice made in the theory. GU makes a specific choice here, resulting in a 4-6 signature for the vertical part of the chimeric bundle. Signature tells us about the number of positive and negative directions in our space.
The signature of the metric on the chimeric bundle is absolutely crucial because it directly determines the kinds of spinor representations possible on this space. And spinors, as we know, are essential for describing matter particles.
Step 9. Choosing a signature is so important because of the math rules governing spinors in a space with a given signature. The 4-6 vertical signature and the 1-3 spacetime signature combine, giving a total signature of 7-7 for the relevant space. Interestingly, GU could also have worked with 5-9. The dimension of the real spinor representation for signature PQ is 2 to the power of floor, P plus Q2. So for 7-7, that's 27 equals 128. This 128-dimensional spinor representation beautifully splits into 2 chiral Weyl spinor representations, each with split signature 32,032. This is a remarkable match. The standard model also requires these chiral spinor representations. Same holds true if we'd chosen 5-9, by the way.
The fact that mathematically natural signatures arising in GU lead to spinor representations of the right dimensionality and chirality to accommodate the standard model fermions, that's a powerful hint this framework might be on the right track.
Step 10. Defining spinors without a metric. This is where lots of previous steps converge. The spinor bundle on our chimeric bundle decomposes based on its vertical and horizontal parts. There's this exponential property of spinors. When you have a direct sum of vector spaces, the spinor representation on the sum relates to the tensor product of the spinor representations on the individual spaces. When we use our observation map to pull this structure back down to spacetime, we find the spinor field decomposes into tensor products of spacetime spinors, how particles behave in spacetime, and internal quantum numbers, other properties like charge. This is exactly what we need for standard model fermions. The vertical part contributes internal symmetries. The dual horizontal part gives spacetime properties. Crucially, this means spinors can be defined in the observer space y14 before we even pick a specific metric on our base spacetime x4.
This is a profound and elegant result. Suggests the fundamental building blocks of matter might exist in a more primordial pre-spacetime setting, and that spacetime and its metric emerge later, along with the specific properties of these particles.
Step 11. The structure group. The fundamental symmetries of the theory, the structure group, originate from the spinor representations of that spin 7 group we mentioned. which came from combining signatures of chimeric bundle parts. Now, choosing 1 and 3 for space-time signature, that's a choice within the theory based on observation. We need a structure group with representations capable of describing both force carriers, gauge fields, and matter particles, fermions. Spinor representations of spin 7s fit this bill. A structure group is essential. It tells us how the internal spaces associated with our bundles twist as we move around in the base space.
The structure group encodes the fundamental symmetries. The fact spin 77 has representations for both bosons, force, and fermions, matter, of the standard model is a significant point in its favor as a potential unifying framework.
Step 12. The inhomogeneous gauge group. Instead of directly using the standard model's gauge group, which is compact, GU uses a larger non-compact group. What's interesting, the maximal compact subgroup within this larger group contains the standard model group SU3, SSU2, AU1. Powerful. Suggests the familiar standard model symmetries might arise naturally as part of a larger, more fundamental structure. This larger group, calligraphic G, is a semi-direct product of gauge transformations. Calligraphic H, smooth ways internal spaces rotate transform, and translations in the space of connections. Calligraphic scripted N. Analogous to how the Poincaré group combines Lorentz transformations, space-time rotation boosts, with space-time translations. But here it's in the context of gauge theory, describing forces.
Constructing this larger inhomogeneous gauge group, which naturally incorporates the standard model group, is a crucial step towards deriving observed particle symmetries from a more fundamental principle.
Step 13. Write action on the affine space of connections. Okay, the space of all possible connections, calligraphic A, which describe how things change as we move around, isn't a standard vector space. It's an affine space, no natural origin. Gauge transformations, those internal symmetry transforms, act on these connections in a specific way. Transforming a connection involves both a rotation term and a correction term. This ensures the covariant derivative, a key tool for calculus in curved spaces or with gauge fields, behaves properly under these transforms. Think about the gluon field in QCD, strong force. Different gauge configurations can describe the same physics. They're related by gauge transforms. Those transforms are a redundancy in description. The specific connection choice itself is not redundant.
The affine nature of the space of connections is key in gauge theory. Gauge transformations represent redundancies in our math description. The connections themselves carry the essential info about the forces.
Step 14. Gauge equivariant map. Eric Weinstein's approach involves seeking a specific kind of map, connecting this inhomogeneous gauge group, calligraphic G, to the space of connections, calligraphic A. This map needs a special property. Equivariance under that right action we just discussed. The seemingly abstract condition turns out to relate to the cosmological constant, that mystery energy density of empty space within GU.
The existence of such a gauge equivariant map would provide a deep, fundamental link between the theory's underlying symmetries and the geometric structure governing the fundamental forces.
Step 15. The augmented torsion tensor, a key GU concept, acts as a gauge equivariant analog of Einstein's contraction operator, defined on our larger space Y14. Cleverly combines aspects of gravity, specifically torsion, a kind of space-time twisting, with gauge theory ideas, covariant derivatives. Importantly, it's built to maintain gauge covariance, something standard GR struggles with. The augmented torsion tensor is essentially an attempt to bridge the conceptual gap between gravity and other forces, making Einstein's theory speak the same mathematical language as Yang-Mills.
The augmented torsion tensor is a central innovation in GU. Attempts to overcome inherent difficulties in unifying gravity, geometric, with other forces, gauge theories.
Step 16. The Schiab operator, introduced by Weinstein, generalizes how Einstein contracts the Riemann tensor to get reach A, but does it respecting gauge covariance. Takes a gauge covariant 2 form as input, produces another form that transforms correctly under gauge transforms, addresses the problem that Einstein's original contraction, using the metric, doesn't play nice with gauge symmetries. The Schiab operator explicitly includes the gauge transformation in its definition. It respects a decomposition similar to traceless parts of the Einstein tensor, but compatible with gauge structure. Simple example, U1, gauge theory, like electromagnetism. Schiab operator acting on the relevant curvature 2 form yields something like the gauge invariant electromagnetic field strength tensor. It's all about building a tool that consistently blends spacetime's geometric structure with force's gauge structure.
The Schiab operator is a vital mathematical tool within GU for constructing gauge invariant quantities from curvature tensors, crucial step in formulating a unified field theory.
Step 17. First order action. The fundamental principle governing dynamics, the action principle, in GU, shares traits with both Einstein-Hilbert, gravity, and Chern-Simons, topological field theory. Unlike Einstein-Hilbert, second derivatives of metric, GU action is first order in derivatives. Fundamental variables are omega, encompassing a gauge transform epsilon, and a gauge potential, variational pi. First part of the action combines augmented torsion tensor with curvature via the GAB operator, generalizes Einstein-Hilbert and Yang-Mills actions. Second part is a mass term for torsion, controlled by coupling constant kappa. Because augmented torsion is inherently gauge covariant, it can be used directly in the action. Unlike gauge potential connection in standard theories, for every element of the inhomogeneous gauge group, the theory effectively defines two connections, A and B. Their difference is torsion T. At this initial stage, the theory is purely bosonic, describes force carriers.
This action principle is the fundamental starting point for deriving the equations governing all fields within GU. Its first-order nature and use of gauge covariant quantities are significant departures from traditional approaches, have important implications for the theory's properties.
Step 18. Field equations. Applying the principle of least action to that action gives the field equations. Tell us how fields evolve, interact. These involve the GAB operator acting on curvature, and the augmented torsion term, p omega, coupled with constant kappa, also a term E from mathematical consistency needs of the variational principle, sort of like an error correction term.
These field equations are the core dynamical laws of GU, describing how the fundamental fields relate and evolve over space and time.
Step 19. Fermion fields as spinor-valued forms. Okay, now to bring in matter particles, fermions. GU describes them using spinor-valued forms. Specifically, a spinor-valued 0 form, just a regular spinor field, and a spinor-valued 1 form has both spinor and vector-like properties. This leads to an operator resembling both Dirac, standard fermions, and Rita-Schwinger, spin-72 particles. It couples the bosonic and fermionic sectors. Eric Weinstein draws an analogy here to supersymmetry, the idea of a deep link between bosons and fermions. Though he stresses it's not the full supersymmetry algebra, just the general idea of interchanging these particle types.
Introducing fermions this way as spinor-valued forms is crucial for incorporating matter into GU's geometric framework. The supersymmetry analogy suggests a potential deep connection between fundamental forces and fundamental matter constituents.
Step 20. Deformation complex. A mathematical structure helping understand the theory's behavior around a given solution. It's a sequence of mass spaces and operators with a crucial property. Apply the operator twice, get 0, d squared equals 0. This property ensures linearized fluctuations around a solution are gauge invariant, don't depend on specific gauge choice. The cohomology of this complex classifies physically distinct ways a solution can change slightly, not just gauge transforms.
The deformation complex is a powerful math tool for analyzing stability and physical degrees of freedom of solutions in a gauge theory like GU. The d squared equals 0 property is fundamental for ensuring consistency at the quantum level.
Step 21. The seesaw mechanism. Interestingly, within this Dirac or Rita-Schwinger-like structure, a mathematical feature emerges mirroring the neutrino seesaw mechanism. In neutrino physics, this explains tiny neutrino masses by postulating very heavy, unseen neutrino partners. Mixing light and heavy states results in observed light neutrinos having tiny masses. Similarly, in GU, the fermionic operator structure leads to mixing between different spinorial sectors. A 0 block in a part of the math matrix allows for large mass scale differences between fermion types, potentially explaining why the 3 generations have such different masses.
The spontaneous emergence of a seesaw-like structure in GU's fermionic sector is compelling, could provide a natural explanation for observed mass hierarchies among fundamental particle generations.
Step 22. Analyzing the structure group reduction. Remember, our initial symmetry group was related to spin 7-7. To connect with the standard model, SU3 to SU2, SU1 symmetry, we need to see how this larger group can be reduced or broken down. Happens via intermediate subgroups. Start with spin 7-7 acting on 128D spinor representations. These split into 2 chiral parts. For theoretical reasons, like Coleman-Mandula theorem suggesting compact internal symmetry for consistent QFTs, and a lack of experimental evidence for non-compact internal symmetries. Reduction to the maximal compact subgroup, spin 7, S-spin 7, is favored. This reduction then proceeds in steps, symmetry breaking at each stage. These could correspond to important phase transitions in the early universe. Might even lead to new physics, testable predictions. Example, one intermediate step involves reducing from a group containing SU4 down to SU3, SU1. This could relate to separating leptons and quarks.
This step-by-step reduction of the structure group is crucial for linking GU's fundamental symmetries to the standard model's well-established ones. The pattern of symmetry breaking at each stage could have profound implications for the universe's history and evolution.
Step 23. 3 generations from the complex. Here's a fascinating result. That Dirac-Rita-Schwinger complex we mentioned, when considered on the observer space Y14, naturally yields 3 distinct sets of fermions. The complex involves a spinor-valued one-form acted on by operators, including one using the Shiab operator, effectively reducing its dimension. Seems this specific complex is a novel introduction by Eric Weinstein. Interestingly, the scalar spinor, zero-form part, gives one set of fermions identified with first generation. The vector spinor, one-form part, then splits into 2 components, gamma trace and gamma traceless parts. These correspond to second and third generations. Each set has 16 components.
The emergence of precisely 3 fermion generations from this complex's mathematical structure is a remarkable achievement of GU, directly addressing a long-standing standard model mystery, the seemingly arbitrary number of fermion families.
Step 24. The Higgs field in GU isn't put in by hand. It arises naturally from the gauge potential, that variational pi we mentioned earlier. Decomposing this gauge potential according to Y14 splitting reveals a component with all the right properties to be the Higgs. Remember, gauge potential is a one-form on Y14 valued in the Lie algebra of our gauge group U, 64,064. When pulled back to spacetime X4 via observation map, it decomposes. Alpha, Yang-Mills fields like photons, gluons, and phi, scalar field, Higgs candidate. Specifically, the vertical part of Y14's tangent vector, metric variations, corresponds to this scalar field phi, a symmetric 2 tensor. The trace part of this symmetric 2 tensor, unchanged by rotations, transforms as a scalar under diffeomorphisms, smooth coordinate changes, just like Higgs should. Furthermore, under gauge transformations of the full structure group G, this trace component transforms in the adjoint representation, also expected for Higgs.
This provides a compelling geometric origin for the Higgs field, linking it directly to the theory's fundamental gauge structure, not adding it as independent.
Step 25. Trace and traceless contributions of symmetric tensors are crucial here. Any symmetric tensor, like our Higgs candidate, can be decomposed into a trace part, sum of diagonal elements, and a traceless part. In GU, the traceless part of this symmetric tensor is associated with the spin-2 graviton, hypothetical gravity mediator. The trace part, the scalar component, gives rise to the Higgs field. Suggests a very deep, fundamental relationship between graviton and Higgs, different aspects of the same underlying geometric object on the Y14.
This intimate connection between seemingly disparate fields' gravity and Higgs mechanism is fascinating, a potentially profound prediction of GU, hinting at deeper unification than previously conceived.
Step 26. Natural quartic potential for the Higgs is also remarkable. Arises naturally from a term in the action looking like Yang-Mills, all C squared. But when expanded and contracted appropriately on Y14's vertical subspace, it leads to a potential energy function for Higgs with a characteristic Mexican hat shape. This specific potential shape is crucial for spontaneous symmetry, breaking how particles get mass via Higgs interactions.
The correct Higgs potential form, essential for the mechanism, emerges naturally from GU's underlying structure. That's powerful evidence in its favor.
Step 27. Yukawa coupling derivation via minimal coupling. Yukawa terms in standard model give fermions mass via Higgs interaction. In GU, these terms arise from the principle of minimal coupling. It involves taking the Dirac operator, describes free fermions, and modifying it by coupling to the full gauge potential on GU's spinor bundle. When we expand this coupled Dirac operator using the decomposed gauge potential, including the phi component identified as Higgs, we naturally get the Yukawa coupling term describing fermion-Higgs interaction.
Provides a geometric origin for Yukawa couplings, linking fundamental particle masses to Higgs interactions within GU's unified framework.
Step 28. The correspondence between the Higgs and the Yang-Mills sectors. Comparing the math structure of GU action's Yang-Mills Dirac part with the Higgs Yukawa sector part, we find surprising deep correspondences. Kinetic terms, how fields move change, quartic terms, four-field interactions, quadratic couplings, mass-related, even how fermions interact, show remarkable similarity. Because Higgs in GU isn't fundamental itself, but a component of the gauge potential. After pullback to spacetime, it behaves like a scalar field.
This profound correspondence highlights the unification GU achieves, where seemingly distinct physics sectors, force-carrying Yang-Mills fields, mass-generating Higgs field, are revealed as different facets of the same underlying geometric structure.
Step 29. The missing quadratic term. A puzzle in Einstein's original GR absence of a quadratic curvature term in the action. Yang-Mills theories, gauge theories, do have quadratic terms in their field strength tensor, a curvature form. In GU, the augmented torsion tensor, analogous to field strength, naturally requires quadratic interactions to maintain gauge covariance. while still allowing the Einstein-like contraction giving gravity.
Addresses a long-standing asymmetry between our descriptions of gravity and other forces, suggests a fully consistent unified theory might need modifications or extensions to standard formulations of both.
Finally, step 30, the emergence of the cosmological constant and CKM matrix. Remarkably, the cosmological constant, that constant energy density driving accelerated expansion, and the CKM matrix governing quark flavor mixing, also emerge from components of the gauge potential, variational pi, after pullback to spacetime. The gauge potential decomposes into parts giving standard model gauge fields, Higgs field, a constant term in Einstein's equations, identified as cosmological constant, and components describing quark generation mixing, CKM matrix. These fundamental parameters aren't put in by hand, arise intrinsically from the geometric structure. Specifically, component variational pi sub lambda corresponds to cosmological constant. Another, variational pi sub CKM, gives quark mixing angles.
The potential to derive fundamental constants and parameters, cosmological constant, quark mixing matrix directly from the underlying geometry is a powerful indication of the depth and unifying power GU aims for.
Okay, wow! That was a rapid journey through a truly ambitious, intricate theory. Geometric unity is certainly a complex landscape, and we've covered a huge amount of ground in this deep dive.
Indeed. Our aim here was really to provide a structured overview, foundational principles, mathematical framework underpinning GU's attempt to bring together the Standard Model and Einstein's General Relativity.
The core idea at its heart is just incredible, isn't it? Start with a simple 4D space. Then explore the incredibly rich geometric structure inherent in the space of all possible ways to measure distance angles within the observer space. From this seemingly abstract start, the theory attempts to derive the fundamental building blocks and interactions governing our universe.
That long-sought goal of a theory of everything, it's always been about finding underlying simplicity to explain apparent complexity. GU seeks that elegance in the language of math and geometry.
And it's quite something to consider how many key features seem to potentially arise from this framework. The specific standard model gauge symmetries, 3 generations of particles, the Higgs field and its potential, Yukawa couplings giving mass, even fundamental parameters like cosmological constant and CKM matrix all emerging from the geometry.
It's important to remember this has been an introductory exploration. The original work on GU delves into much more advanced topics: how Dirac and Klein-Gordon equations arise, CKM matrix unitarity, ensuring quantum consistency, much more.
It really makes you wonder, doesn't it? Could the sheer complexity of the universe we observe be just a reflection of incredibly intricate geometric structures hidden within seemingly simple mathematical objects?
That's a profound question, precisely the kind of perspective a theory like GU encourages. Perhaps the apparent complexity is just the unfolding of a deeper, more elegant geometric reality we're only just beginning to glimpse.
This has been a deep dive into the fascinating, complex world of geometric unity. Stay with us on the deep dive for future explorations into other equally intriguing and challenging topics.